I consider any small portion of a body here, and that is represented here dA. So these two types of forces are acting. One is normal to the area, that is the pressure force, and one is parallel to the area, that is the shear force and the pressure force. Because we are interested to calculate what is the force acting in x direction and what is the force acting in y direction, this is how we try to define the lift and the drag forces. So we resolve these two types of forces, such as the pressure and the shear forces, on small element into components, taking the orientation. So for this given setup, we come up that the differential force dF acting on this area dA in x direction, that is equal to PdA into cos of theta and tau W dA into sine of theta, both in the positive x direction, so carry positive sign. And similarly in the y direction, this is equal to minus PdA into sine theta, because its component is down in the y direction, so that's why the negative sign, and plus tau W dA into cos of theta. So if we are interested to calculate the total force, then we have to integrate these equations. So we will get the total force for that body, and similarly the total lift force acting on the body. Clear? So as I said, that it is very difficult to calculate for the differential areas of the body, the shear stress and the pressure acting on that. So that's why we defined the lift and drag coefficients, clear, which are dimensionless. So the lift and drag coefficients are dimensionless forms of lift and drag. So the drag coefficient, this is defined as, denoted by C with the subscript D, is equal to FD divided by half rho V square into A. Similarly, the lift coefficient, it is defined as CL is equal to FL divided by half rho V square A. So in these two equations, A is ordinarily the front area, the area projected on a plane normal to the direction of flow of body. So in this case, the drag coefficient, this area A, that will be the frontal area. That is the area projected on a plane normal to the direction of flow. Clear? For example, if I go back here and show you the example here, see this one. But this is now a plane which is perpendicular to the flow. So this is the body. So if you want to take that area, it will be projection of that, as you study. In drawing, you can see the projection of this area on this plane. So this is the projection of that area. Clear? This dimension multiplied by the width that is perpendicular to this plane. Clear? So that will be the area that you have to consider to calculate the drag coefficient, projected on a plane perpendicular to the flow. Clear? So this is what we say here, that this A is ordinarily the frontal area, the area projected on a plane normal to the direction of flow. In lift calculations of some thin bodies such as airfoils, A is taken to be the plane form area, which is the area seen by a person looking at the body from above in direction normal to the body. Clear? So the plane form area means that if I go back to that figure, so you can see here the plane form area. You look from above, so how this area will appear? Clear? This will appear like this to you. If I extend this, so you can see here this area will appear like this, plane form area. This is how you look to this from the top. So for the lift calculation, then in that case, this dimension we have to consider for this body. So this is how you will calculate the area, clear, in these equations. To calculate the drag coefficient and the lift coefficient, they are given as Fd divided by rho v square into A into half. So now in this case, the thing is, if you want to calculate the drag coefficient, we need to calculate the drag force. This is the property of the fluid. Velocity is the velocity of the body or the fluid, the free stream velocity, and A is the area that I explain how to calculate. So now how we can calculate, let's say, this drag force. This we already discussed. Clear? If you remember, I discussed it already here. The drag force can be measured directly by simply attaching the body subjected to fluid flow to a calibrated spring and measuring the displacement in the direction of flow. So this way we can calculate the drag force, and then in that case we can put here in order to experimentally determine the drag coefficient. Clear? Or if the drag coefficient is known to us for any body and the lift coefficient are known, we can calculate the lift and drag forces using these equations. Because this equation you can use to calculate the drag force if CD is known. So then in this case what will happen? That this FD, so this will be equal to CD into rho V square by 2 into area A. We can conveniently use these expressions in order to calculate the drag forces, provided the drag coefficient is known to us. So this is a convenient way to calculate these forces, because in this case then you have to evaluate these integrals for the differential areas of the bodies, which is very inconvenient. Clear? Now in this equation, this half rho V square, this is actually the dynamic pressure. This term half rho V square is the dynamic pressure. And you have studied about the pressure, you have studied a chapter fluid measurements in your fluid mechanics 1. You might have studied about the static pressure, dynamic pressure, stagnation pressure. So just to refresh your memory, I will just briefly talk about this, not in detail. You might have studied about them in flow measurement or pressure chapter when you especially studied the pitot tube. There these terms are frequently used. Clear? Flow measurements. Now in this case what we have is that, let's say we have a fluid which is flowing, and then you have a piezometer. So the piezometer, it calculates the static pressure for you. Clear? You already have studied. And when you insert a pitot tube which has L shape, clear, this is pitot tube developed by Henry Pitot. So what will happen, that the liquid will rise in the pitot tube. You can see here the piezometer which shows the static pressure. This stagnation pressure, it is given by the pitot tube, because this is the stagnation point here. Because at this point what will happen, that the fluid, when it is moving with the velocity v, but when it reaches here at a stagnation point, what will happen, that this velocity will be equal to 0. And this velocity, because this fluid, liquid or fluid is moving with kinetic energy, but that kinetic energy is now converted into the pressure energy. And that's why you can see here that the water will rise to this level in the pitot tube here. Clear? So this term, this is known as the dynamic pressure that we are using here, half rho v square. This is the dynamic pressure. Clear? So now it means that the stagnation pressure, this is actually the sum of static pressure plus the dynamic pressure. Clear? So stagnation pressure is more because this is equal to sum of the static pressure plus the dynamic pressure. And then once we can measure the static pressure, then you can see here that this dynamic pressure concept, this is used in order to calculate the velocity. And this is the basic purpose of this pitot tube. We are using pitot tubes to measure the velocity of flow. So the sum of static and dynamic pressures is called the stagnation pressure, and it is expressed as P stagnation, which is here, P stagnation, that will be equal to the static pressure, which is here, and plus this term which is known as the dynamic pressure. So this diagram is available in your textbook in chapter 11, I think, flow measurements, when you discuss pitot tube. So you can see here that if we consider 2 points here, one is point M and one is point N. So in this case, you can see here that if you insert a piezometer, it will show you the pressure head, the static pressure. Clear? It will show you the static pressure here. And when we insert a pitot tube, L-shaped tube, then it will give us P naught by gamma, the stagnation pressure head. Clear? And difference of the two is your U square by 2G. Again, this U, because this U means velocity in the X direction. That's why U is used. Clear? Because the velocity can have Y component and Z component. But specifically here we talk about the X component, so that's why this U is used, which I clarified in the beginning of this chapter. Clear? But we will prefer to use V to be consistent with what we have studied so far, to avoid any confusion, but you should know the concept that why in books U is used. Clear? So for example, how this equation comes, this we can apply the energy equation, Bernoulli equation, at point M and at point N. So what will happen, for example, if I can write down here, so we have P by gamma. Clear? At this point you have P by gamma, the pressure, which is indicated by this piezometer. Then we have U. So since the liquid is moving with a velocity U here, it is undisturbed. So that's why we can say that this is equal to U square divided by 2G. Then we have Z at that point. So let's say we have Zm, the three forms of energy that we consider. And then at point N, what we have is P naught by gamma. This is the pressure which is measured by here. So this is equal to P naught by gamma. And what about the velocity? This will be equal to U square by 2G. Let me just write down first. So we have U square by 2G, and plus we have Zn, means elevation of this fluid at N. Clear? Okay. So now we consider this one. Now let us simplify this equation. So simplification means that when a fluid reaches at this point, just outside the entrance to the pitot tube, so it is brought to rest. So that's why this velocity is 0 at this point here n. Since point M and point N, they are at the same level, so that's why this and this cancel out. Clear? They are equal. So now what we are left? We are left with P by gamma. What we are left? We are left with P by gamma plus U square by 2G is equal to P naught by gamma. And this is what you can see here in this diagram. P by gamma plus U square by 2G is equal to P naught by gamma. So now if I want to write down in this fashion, then what you can do is that this equation you can write down as P plus multiply both sides by gamma. So we have gamma U square divided by 2G is equal to P naught. And then gamma by G, so that is equal to rho, because you studied that gamma is equal to rho into G. Clear? So now this expression we can write down here. P naught is now the stagnation pressure is equal to P and equal to rho V square by 2. Clear? Because in this case gamma will be equal to rho will be equal to gamma by G. Clear? So in this case rho is equal to gamma by G. Is this correct? So this will be equal to rho V square by 2. Clear? This is how it comes. So this is the concept of static, dynamic and stagnation pressures. So this is how it is written here in these equations, that CD is equal to FD. Clear? CD is equal to FD divided by half rho V square into A, and CL is equal to FL divided by half rho V square into A. So now these are convenient forms that we can use to calculate the drag and lift coefficients, and also if conversely we know these coefficients, so we can conveniently use these equations in order to calculate the drag and the lift forces. Otherwise then you have to integrate these equations, which is not a convenient way in order to calculate the drag and lift forces on bodies. Clear? Now friction and pressure drag. So far we studied about the drag and lift forces. Clear? But as you can see here in this equation that I try to explain is that you have this drag force, but in this drag force it has two components. One is due to the pressure and one is due to the shear. Clear? So now because this is equal to summation of two components, now we talk about this friction and pressure drag. There are two components which sum up to form the total drag force. So the drag force is the net force exerted by a fluid on a body in the direction of flow due to the combined effects of wall shear and pressure forces. As we saw earlier, that drag force is the net force exerted by a fluid on a body in the direction of flow due to the combined effects of wall shear and pressure forces. So the part of the drag that is due directly to wall shear stress is called the skin friction drag, or just the friction drag. So if that portion of the drag which is due to the wall shear stress, that is simply known as the friction drag, or also called as the skin friction drag, since it is caused by frictional effects. The part of the drag that is due directly to pressure is called the pressure drag, also known as the foam drag, because of its strong dependence on the form or shape of the body. So here what we say is that if I come back here, because this is due to the pressure, this component here, so that's why this is known as pressure drag. This is known as pressure drag. And when it is due to the shear stress, then it is known as the friction drag. So this is what it says, that this is the pressure drag, this one. This is due to the pressure. So we call it that this is pressure drag. And this component which is due to the shear stress, this is known as friction drag. This is known as friction drag. So this pressure drag plus friction drag, pressure drag is also known as foam drag, or this friction drag is also known as skin friction drag. This will make up the total drag on the body. This will make the total drag. So the friction drag coefficient, it is denoted by CF, and it will be equal to FF, this friction drag, divided by half rho V square into A. And the pressure drag coefficient will be equal to Cp equal to Fp divided by half rho V square into A. And then the total drag, this will be equal to Fd equal to F of F plus Fp, the friction drag force plus the pressure drag force. Clear? So now contributions of the pressure drag and the friction drag for various shapes. As you can see here, when we have a thin plate, thin object which is placed, you can see here in this case, the pressure drag is 0, because here you can see here the direct impact of this velocity on the object shape is very small, normal. So that's why it is very, very small, 0%. But you can see as the fluid moves on this body top and the bottom, then significant resistance can offer due to friction, and that's why the friction drag is significant. Similarly, you can see here now in this case, the pressure drag is approximately 10% and the friction drag is 90%. Now if we place a spherical object, then in that case you can see the pressure drag is approximately 90% and the friction drag is 10%. And if you see that you hold a plate perpendicular to the direction of flow of fluid, then in that case you can see here that the pressure drag will be significant. And where will be the friction drag? It will be just these sides, top and bottom, negligible. So that's why we can say that pressure drag is the major force acting on this body, and friction drag has little to no contribution. Clear? So that's why earlier we stated about the shapes of the body, that the shapes of the body, they play important role. Now you can see here we continue with the discussion of friction and pressure drag. So now we will discuss drag in detail, and then later on we will discuss lift in detail. Clear? Now you can see here that drag is due entirely to friction drag for a flat plate parallel to the flow. Now in this diagram you can see a flat plate which is placed parallel to the flow. It will have width perpendicular to this plane. You can see here that on the top surface here the friction is significant, similarly at the bottom. So that's why drag is due entirely to friction drag for a flat plate parallel to the flow. If this same plate is held perpendicular to the flow, you can see here this is now the plate. So now in this case it is due entirely to pressure drag for a flat plate normal to the flow. You can see the friction will be just here at the top and at the bottom, which is very small. So the greater portion will be that of the pressure layer, which is acting perpendicular to this surface pressure. So that's why it is written that it is due entirely to pressure drag for a flat plate normal to the flow. So you can see here the shape of the body and orientation of the body plays important role. And if we consider a cylinder, this is now a cylinder which is placed in this flow. So it is due to both, but mostly pressure drag for a cylinder normal to the flow. So in this case you can see here that from the front it will hit this, and also at the surface as it passes and moves in this direction. Clear? So that's why it is due to both, but mostly pressure drag as compared to the friction drag for a cylinder normal to the flow. So the total drag coefficient CD is lowest for the parallel flat plate, highest for a vertical flat plate, and in between but close to that of vertical flat plate for a cylinder. Now measuring the drag coefficient for a car, we earlier discussed here that this one here, the drag coefficients. So how we can measure them? For this you need to measure these parameters, then we can able to calculate this. And once if we know for different bodies the coefficients, the drag coefficients and the lift coefficient, then we can directly use this formula to calculate the drag forces. So now we are looking how to calculate experimentally this drag coefficient. So we here consider an example. Clear? That measuring the drag coefficient of a car. So what we do here is just an example. The drag coefficient of a car at the design conditions can be determined experimentally in a large wind tunnel in a full-scale test. So what we can do here is that we have wind tunnels. Clear? These tunnels are constructed large wind tunnels where models and prototypes of cars, trucks, aeroplanes, they are tested. Clear? Those manufacturers who manufacture cars, aeroplanes, etc., trucks, they do testing on their cars, the shape, etc. Clear? So for that purpose, they have these facilities available with them where they can carry out full scale tests or on models, small scale tests. Clear? So what you can do here is that through the tunnel, then what will happen? Air will be allowed to pass. So this is how you know the velocity V, that with which velocity the air is flowing. So definitely it will exert a force, drag force on this car, and that drag force we can measure by this facility here. Clear? Because it can measure that how much force is exerted on this car. So we can calculate this FD. And the area, as we already discussed, that you can approximately calculate for this car. And once we know this VFD and the area in this equation here, the area, the velocity, and FD, then we can calculate the drag coefficient. Clear? So this is an experimental setup how we can proceed to measure the drag coefficient. Clear? Now, based on this concept, what we have done is that you will find these drag coefficients for different shapes of different bodies considering the reference area. These drag coefficients are calculated. For example, for parachute, if you consider the frontal area to be pi by 4 d square, then the drag coefficient is 1.4. So if, for example, we have this problem in parachute and you are asked to calculate the drag force, you can calculate the frontal area by this equation. And you already know the density of the air. If, for example, temperature is given, you can read it from the tables, etc. The velocity with which it is moving. So this drag coefficient you can use to calculate the drag force which is acting on this parachute. So similarly, the problem in order to calculate the drag force depends on how the area is considered. Clear? So you can see here that if the flow is in this direction, from left to right here you see, then these are the values, and from right to left these are the values. Clear? So these tables you will find in the books when you study this chapter. These coefficients are developed, drag coefficients, clear, for different objects such as shown here. So these we can use in order to calculate the drag forces. Clear? And these are experimentally determined coefficients. Similarly, here you can see that for bikes, if upright commuter, you can see here the drag coefficient is 1.1. But in the racing, you might have seen that the person is bent. So the thing is to reduce the area. Clear? And when we reduce the area, so the drag force that will reduce, because you can see here in the equation what is the drag force, FD. So FD is directly related to this area A. So small is the area, small will be the drag force. So that's why in this case what is happening, that the area is reduced as compared to here. So you can see here the drag coefficient is small as compared to this value. So if you further move to streamline here, you can see here the drag force coefficient is further reduced. So it means that streamlining the objects, this is what we started with, blunt bodies and streamlined bodies. If we are streamlining the bodies, then we are able to reduce the drag coefficient, means we are able to reduce the drag force. And when the drag force is reduced, what it means that the body or the object, it will move faster. So when it moves faster, it will be fuel efficient, clear? Because it will cover more distance. Now you can see here, for example, for trucks. So you might have seen this arrangement here. As compared to the standard, you see the drag coefficient is 0.96. But with slight modification, the drag coefficient is reduced to 0.70. And you can see here, for example, for a dolphin, the drag coefficient is very, very small. Clear? For large birds, it is around 0.40. That's why they are able to move faster. Clear? So based on this concept, what we are doing, that we are streamlining. We are trying to streamlining. That's why you see the front of the aeroplane is made oblong in order to reduce the drag force. Clear? So you can see here for cars, so CD is 0.4. But now by streamlining, you can see the drag coefficient, it is reduced from 0.4 to 0.3. This is what I give you an example earlier. So that's why here, to move with the same speed, this vehicle to move with the same speed as this vehicle, it will require less power. Clear? For high-rise buildings, so A is the frontal area that we need to calculate, and CD is 1.4. So we can estimate the drag force, wind load, which will be acting on this building. Clear? Next, we have drag on three-dimensional bodies. So again, the concept is that total drag, that will be equal to the sum of the two components. One is the friction drag and the second one is the pressure drag. The same concept applies for three-dimensional bodies. Clear? So in this case, you can see here in the figure that we are trying to streamline the bodies. And earlier we stated that the flow past a car that is three-dimensional. You saw in the picture, the flow is three-dimensional. And we are very much interested because we are using cars in our daily life for transportation purposes. So we want to make them more efficient, move faster, more fuel efficient. Clear? So you can see here that since 1930s, we have been able to reduce the drag coefficient, because more the drag coefficient, more the drag force. So you can see that since 1930s, we are able to reduce the drag forces. Clear? So this is the historical trend of streamlining automobiles to reduce their aerodynamic drag and increase their miles per gallon. So because of streamlining, what we are doing is that we are able to reduce the drag coefficient, and this help us to reduce the drag force acting on the moving cars. And because of reduced drag, they can move faster or increase their miles per gallon. So now I show you a small video. You can see the difference of this streamlining. So you can see that in model A, the shape, more drag will be created on the body, Okay, so I'm sorry. I think the computer restarted when I played the video. Oh, sorry for that. Let me start again.